In the case of multiple standard additions, we're going to end up plotting the signal against the volume of the standard that we're adding. So we ask the volume of standard or spike against the signal, and you'll get a straight line, hopefully, where when the S is 0, it's just the analyte, and then you add increasing amounts of the standard to it. And we can fit a straight line. And it turns out that when you do that where the signal equals 0, which is right here, this intercept value, that's equal to the equation minus Ca, the concentration of the analyte, times V0, the volume of the sample in the standard addition solution, divided by the concentration of the standard. Okay, we can actually think of this this distance here between Vs equals 0 and the intercept value is kind of like the volume of the standard, which has the same number of moles of analyte as the sample does. That's another way to think about it. The way to get that number, and just remind you again, for standard addition, we have a volume of the sample, and then we're adding a standard to it. So we have some volume of standard, and we're going to make all these standard additions up to the same total volume. And this will be the concentration of analyte, and then the standard is C standard, concentration of the standard. So to get this intercept value, we make the best straight fit line. So let's say the best straight fit line, the equation of the line is 5.86 times x plus intercept of 2.04. What we have to do, or what we can do here, is just set this equal to 0. So we're saying the y value of the signal is 0, and then rearrange for x, and we'll get that that is negative 2.04 divided by 5.86. And you get a value, in this case, of negative. It's still going to be negative for a negative value, and 3.348. And the units of this is going to be milliliters, or if you're measuring liters, it would be liters, whatever the volume unit is. So now we can set that equal to this whole equation. Okay, so let's do that. We can rearrange then for Ca, which is the concentration of analyte, what we're looking for. And we could say that equals 0.348 milliliters times the concentration of the standard divided by the volume of the sample. Now let's say for this particular example that our standard concentration is 1000 milligrams per liter, or part per million, and the volume of the sample is 20 milliliters. We're going to try and keep these units consistent, so we have milliliters here and over here, so they're going to cancel out, and we'll end up with an answer for concentration which is milligrams per liter. And we'll just do that calculation. So we have, oh, I forgot the negative. Remember, in the equation there's a negative, so these two negatives are going to cancel out. So 0.348 milliliters times 1000 milligrams per liter divided by negative 20 milliliters. Milliliters cancel out, we get milligrams per liter, and so our answer in this case is 17.4 milligrams per liter.